Alright, so last time we were looking at increment and decrement instructions, and we saw that we could use those to just add or subtract one from a register. We also looked at special locations 400 through 407 and saw that we could examine and modify the general purpose registers by using those addresses. And then we ended by saying that, even though sometimes we just want to execute sequential instructions, it can be useful to be able to go back and re-execute sets of instructions that have already happened. And so I want to illustrate jumps and the idea of looping. And by the way, I'm following along with this Touch Metal Practice Problems book, which will hopefully be available soon, but we're working through chapter 4 here, which is on branches and loops. You can find a draft of that book on the Touch Metal site right now, and follow along if you like. Because it's tricky for my document camera to capture this board and also the display, it works a little better if I take out the color. So I'm just going to go monochrome here, and so we can do things like increment a register, and if you remember the increment instruction, we can pull it up on the programming card here. Increment is coded as 10 followed by the register number. So in octal, 100 would say increment R0. So I'm going to go ahead and I'm going to put in a 100 and deposit that in the current location 0. So the first instruction of our program is now increment, and if I do that again, right, I can say deposit, and that's the second instruction. I don't have to keep typing 100 because that's the value of the input register right now. So I can just deposit this in the first 5 locations, and now if I look at location 0, I can see the instruction is increment R0, and that's stored at location 0, 1, 2, 3, and 4. So I have 5 increment instructions, followed by a bunch of no-ops, instructions that don't do anything. And if I examine location 400, I can see that register 0 is currently equal to 0. So if I say step, it's executed one instruction, and if I look at my register, it's incremented to 1. If I say step again, it's incremented to a 2, and I can do that a total of 5 times. The next time that I step, it's executed a no-op, and my register doesn't change anymore. And in fact, if I just say run, and I examine register 0, it's just sitting at a 5. So when I examine, it stops the program from running, but I can go ahead and I can say run, and we can see the program counter incrementing here. Point, if I examine location 400, it's still just 005. So let me go ahead and continue running it, and it did a few increments, and now if I examine, I can see R0 is 12. That's 12 octal, which is 8 plus 2 is 10 decimal, so it incremented 5 more times. So that's a program that is doing the same thing, because it gets to the end of memory and it just jumps back to the very beginning. We can force that behavior to happen ourselves, though, by using what's called a jump instruction. So look at your programming sheet, and there's a bunch of jump instructions starting with JMP address, and that's coded as 004 followed by AAA, and it tells you AAA is an 8-bit address. So if we put the instruction 004 followed by a number, that says jump to the instruction at that location in memory. So let's clear out memory. So I'll do 2 resets, and I'll say 1 to say yes, erase all memory. But I need to change my input register to 0 also. So let me go back and examine location 0. Alright, so 100, I'll deposit that. And then I'll go ahead and say 004 and deposit that. And then I'm going to say 000 and deposit that. Okay, what have I done? Let me take a look at my memory right now. Instruction 0 says increment R0. That's the same as before. If I say examine, instruction 1 says jump to 000. In other words, go back to the instruction at location 0. So if I execute this, I will increment my PC to 1, and it'll say jump to 0. If I say step again, it'll go back to 0 and say increment R0. If I step again, it will presumably do that increment and then say jump back to 0. And if I step again, it'll do another increment and then another jump. And right now, if I examine location 400, I can see my register is 3. So if I simply tell it to run, I can see it doing a bunch of these increments and jumps. And now if I examine 400, it's 27. If I run some more and I examine 400, it's 37. If I run some more and examine it, it's up to 61. So this is a loop. This is saying, hey, go back and re-execute previous instructions. And the only thing we need to make a loop happen is just this jump instruction. Now if I were to put in a different jump, so for example at this location I could say 004, that's a jump, but let's jump to the location 123, and now if I go back and examine location 0, that says increment R0, the next instruction says jump to 123. So if I reset my program counter, that's going to do an increment, I can say step. The next instruction says jump to 123, right? My program counter is 1. When I execute that jump, my program counter is now 123. It's changed where in the memory it is executing instructions, and it's just decided to go ahead and start executing instructions at this other location. So that's the idea of a jump, sometimes called a branch. And basically we can use those to go back and re-execute different sets of code that we've already executed, or code that is not sequential in memory. And this is going to be a really important feature as we start to develop more complex programs.